Hello everyone. Today's topic of discussion is optimal binary search trees. Before we go into the formal discussion of binary search trees, I would just like to define the basic idea behind binary search trees. People who have had a basic course in data structures would be familiar with the idea or concept of binary search trees. A binary search tree is a special binary tree. You could also call it as an ordered tree that satisfies two key properties. We can understand the two properties that a binary search tree satisfies by the following example. This is a very simple example of a binary search tree. Consider this example where 8 is at the root level. Now, any tree or any binary tree, we could define it as a binary search tree if all the values of the nodes in the left subtree are lesser than the value at its root. So if you see the numbers 3, 1, 6, 4, 7, all of them have values which are lesser than 8. On the right subtree, we have all values which are greater than the root node. This pattern would recursively repeat for all the subtrees as well. Consider this small subtree here. 6 is at the root level. To its left, we have 4, which is lesser than 6. And to its right, we have 7, which is greater than 6. The same pattern could be visualized here as well. Assuming a new entry 16 into the tree, 16 would definitely fall to the right of 8, and definitely it would be added as the rightmost node of 14. So such a tree we call as a binary search tree. There are a number of important applications of binary search trees, the most important of them being the implementation of a dictionary. You could consider dictionary as a collection of elements which are ordered, with most important operations being to insert an element or delete an element from the dictionary, or in fact to search for an element from the dictionary. We bring in the concept of optimal binary search trees to discuss the implementation of efficient dictionaries. In order to implement these search, delete, or insert operations efficiently on dictionaries, it is required that the number of accesses or the searches required for locating a key element is the minimal one. This idea of minimizing the number of search operations required for accessing key elements from a dictionary brings in the concept of generation of optimal binary search trees. Now we go to the formal discussion of optimal binary search trees. Assume a very simple example given here. Consider that the keys to be implemented in the dictionary are A, B, C, a set of ordered keys A, B, C, and its frequency count is given as 1, 2, and 3. What do we mean by this frequency count? Frequency count is nothing but the search probabilities of the keys A, B, C. Or it could also be defined as the number of accesses or the number of searches that has happened in the previous history for the element A, for the element B, or for the element C. Based on the past search history in a dictionary, 1 is the number of times that A would have been accessed, 2 is the number of times that B would have been accessed, and 3 is the number of times that C would have been accessed. So you could also count or call them as the search probabilities of the keys A, B, and C respectively. Now, given such key elements, ordered key elements, what are the different ways in which you can construct binary search trees? As seen in the diagram below, I have listed down here 5 different possibilities where the first possibility shows B at the root level. The second and the third shows A at the root level, and the last two show C at the root level. Now, if you consider the first case, if B is at the root level, then as per the property of BST, A could only appear as its left and C would appear as its right. Consider the second case. If A is at the root, then B and C would obviously fall as its right subtree. The third case is a minor variation of the second case in which there is small change in the subtree pattern. Since A is at the root, B and C would fall as a right subtree here, and in this case, C is at the root level here, And since C is at the root level in the subtree, B has to appear as its left. Similar is the case with the last two trees where C is at the root level. Since C is at the root level, as per the property of BST, A and B would definitely fall as its left subtree. If B is at the root of the left subtree, then A would be to its left. If A is at the left of the left subtree, then B would fall to its right. These are the 5 different possibilities of binary search tree construction with the given keys A, B, and C. Now, going to the next step, let's assume that we have to look for certain key elements from this tree. Assume that I'm looking for or locating the key element B. What would be the number of accesses that I would take in order to locate B? B is at the root level, and hence the number of searches for B would be only 1. And what is its frequency count? It is given as 2. Hence, the total number of comparisons required for B would be 2. Consider that I'm looking for A from the BST. A is at level 2. So when I start looking for A, I would have done a comparison at level B and then moved down to level 1. Since there are 2 comparisons involved for locating A, the number of comparisons is 2 multiplied by its frequency count, which is 1. And hence the total number of comparisons for locating A would be 2. Similar is the case with C, where C would have been first looked at the root level and then at level 1. Hence 2 comparisons multiplied by its frequency count, which is 6. Put together, the total cost of this binary search tree would be 2 plus 2 plus 6, which is 10. When applied the same for all these binary trees, we find that case 1, that is tree number 1, and tree number 4, both of them have generated the cost of search operations as 10. So I could call tree number 1 and tree number 4, both of them as optimal binary search trees, since the number of comparisons for locating all the key elements put together is the minimum. This is the concept behind optimal binary search trees. To briefly summarize, we call any binary search tree as an optimal binary search tree in which the average number of comparisons for locating key elements is the minimum. What we've just seen so far is a brute force or an exhaustive method in finding out an optimal binary tree. The same could be very easily solved, very efficiently solved using the technique of dynamic programming. Consider a very simple example given here. A set of keys A, B, C, D which are ordered and their respective probabilities or search probabilities are also given as 0.1, 0.2, 0.4 and 0.3. Now, the aim of the task is to construct an optimal binary search tree using the technique of dynamic programming. Before we start with the solution, it is essential to understand or just have a brief revisit of how a problem is solved using dynamic programming. Dynamic programming is a design technique which tries to solve a given problem by dividing them into a number of subproblems. The key idea behind these subproblems is that the subproblems generated are dependent on each other, or they could also be called as overlapping subproblems. They are overlapping in nature because to solve one subproblem, you require the solution of the previous subproblem. Say that to solve a particular problem, we have divided them into 4 subproblems. Subproblem 2 requires a solution of subproblem 1, and subsequent subproblems, say subproblem 3 and 4, will borrow solutions from subproblem 2 as well as subproblem 1. Hence, such subproblems which are dependent or overlapping in nature is a very common trait in dynamic programming. In other words, you could also say that dynamic programming solves a particular problem in stages where each stage borrow the solution from the previous stage, and each of the solutions generated by every stage are optimal in nature, and hence the final solution would also be considered optimal. Now here is an instance which we're going to have a look in this session with keys being ordered A, B, C, D. Please remember or note that the keys have to be ordered and their respective probabilities are given. OBST could be generated using dynamic programming with the following recurrence. We keep aside the recurrence for quite some time now. Let's go on to solve the problem for stage 1 and stage 2, and we will revisit the recurrence and hence thoroughly define what the recurrence actually means. Since there are 4 keys given in the problem, we have divided the problem into 4 stages. Now, what is stage 1, stage 2, 3, and 4 consider? Stage 1 considers all one-node possibilities of inclusion into the binary search tree. For example, there are 4 cases to be considered in stage 1: C11, C22, C33, C44. Now, what does a C determine? Please have a look at the tables displayed here. There are 2 tables which have to be designed while constructing the solution to OBST using dynamic programming. The first one we call it as a cost table. The second one we call it as a Routh table. The cost table records all the optimal costs of each of the possible binary search trees generated in each of these stages, and the Routh table would define or would record which node, when acting as a root, is generating an optimal cost. The entries would be much clearer once we solve some of the stages at least. So let's look at stage 1. So in stage 1, there are 4 cases: C11, C22, C33, and C44. What does C11 determine? C11 determines the cost of a BST by including only node 1 into the BST. When I refer to node 1, it means key A into the BST. C22 is the cost of a BST by including only key B into the BST. C33 similarly would include only C, and C44 would include only D. So stage 1 explores all the one-node possibilities. Now let's go back to the Routh table and the cost table and find out how we can fill these entries. Okay, so these entries are 0, 0, 0, 0. The diagonal entries are filled with zeros. Now consider the entry 21. Its cost or the optimal cost is entered as 0 because the keys that are chosen to be included into a BST can only be chosen in the order, in an ordered fashion. So to I, consider every entry in this table as Cij. I and J refer to the nodes which are possible inclusions into the BST. So J, this is I, the rows determine I and the columns determine J. J cannot be greater than I, and all such entries where J is greater than I be padded with zeros. Okay. Now this is the first entry in the cost table. Now we would go to define what is C11. As I already told you, C11 is the cost of a BST by including only one node, which is A, into the binary tree, and hence its cost would be naturally 0.1. Similarly, C22 would be 0.2, C33 would be 0.4, and C44 would be 0.3, as is given in the entries here: 0.1, 0.2, 0.4, and 0.3. So what does this 1 and 1 determine? 1 and 1 determines is that there is only one node for consideration in this case, and that is 1. In this case, there is only one node for consideration, and that is 2. Here it is 3, and here it is 4. Now let's have a look at the Routh table. The same entry here in the Routh table, see, you can call it as R11 if required. So this entry would tell you which node, when acting as a root, is giving you this optimal cost. Obviously, in this case, there is only one node which is included, and that has to be A. Similarly, with 2, 2, the only node that has a possibility of inclusion is 2, and its key is B. In this node, the only node that can be included is 3, and its key is C. And in this case, The only node that can be included is node 4 and its key is D. So we have just come to the end of stage 1 of OBST. Now we go on to stage 2, where there are 3 cases to be considered. C12, C23, C34 are the different 2 node possibilities. Remember, I cannot make a choices. I can choose. When I make a choice for nodes, I can do it only in an ordered fashion, and hence 1, 2, 2, 3 and 3, 4. Right? Okay, so let's consider how we solve 1, 2. Now we can have a look at the recurrence, the mathematical recurrence for solving. So coming back to the recurrence here, C determines the optimal cost. I and J are entries which determine what are the nodes that are to be included in the BST. K is a value which will determine which node acts as the root node. As in, when you consider this case, there are 2 possibilities for K. Either 1 could act as a root node or 2 could act as a root node. And our aim is to find out which among 1 or 2 is giving you the optimal BST. Okay. So with the help of this recurrence, we can very easily find out the value of C12. So just to give a brief idea of what this recurrence actually means, Cij, as we have already discussed, we have to find the minimum of 2 entries here. What are the 2 entries here? There will be 2 entries defined by these curly braces. One entry would be K acting as 1 and the second entry would be K acting as 2, where K determines the root node possibilities. So we have to find out the minimum among 1 or 2. And along with this minimum value, we also add the probabilities of these nodes. PS stands for the search probabilities of the key values which we are considering. So S ranges from I to J, where I and J hold the values 1 and 2 in the current instance. So this would be the search probability of key A and key B. So this would be the summation of the search probabilities of the keys that we consider or the nodes that we consider. And this would be the minimum cost that would be generated by either considering 1 as a root node or 2 as a root. So let's quickly write it down here. So assuming K is equal to 1, this would be cost of. So we have defined minimum of, if K is equal to 1, then this entry would be 1, 0 plus cost of K plus 1, so that will be 2, K plus 1, 2, 2. So that entry would be naturally, this entry would be this entry would be C10, which is a 0, plus C22, which is 0.2. Similarly, with the K as 2, K holding the value as 2, this entry as per the recurrence defined, C of I, K minus 1. I is 1, 1, K minus 1 would be 1, C of 1, 1, plus cost of K plus 1, which will be 3, J will be 2. So this entry, as we know, I is greater than J, its entry would be 0, and 1, 1 is given as 0.1. We have not given as, we have identified it as 0.1, and hence 0.1 plus 0. So out of these 2 possibilities, when K is equal to 1 or when A acts as a root node, the minimal cost is, the cost is 0.2, and when K acts as B is the key value or the root value, the cost is 0.1. So minimum among this would be obviously 0.1. 0.1 plus, we add the probabilities of the nodes that are considered. The probabilities would be again 0.1 plus 0.2. The probabilities of the nodes that we consider, that is 1 and 2, would be 0.1 and 0.2. Hence, the total cost would be 0.1 plus 0.1 plus 0.2 would be 0.4. So C12 has been calculated as 0.4. Yes. So similarly, we would repeat the same for all the other entries. Let's assume the case C23. So we have entered this. Please see the colored cells here. This yellow colored cells indicate stage 1 solution. So I have shown the same here. These yellow entries are stage 1 solutions. And now we are in stage 2, where we have found out the solution for C12 as 0.4. Similarly, C23 would be minimum of, now when 2 and 3 are considered, the node possibilities are either k is equal to 2 or k is equal to 3. So when k is equal to 2 or k is equal to 3, the keys that are considered are either B and or C. So with 2 and 3 as the possibilities, we have C of k minus 1, I comma k minus 1. What is I? I is 2 and k minus 1 will be 1 plus C33, 0.4 and 0.2. The minimum among them will be 0.2. So 0.2 plus their search probabilities would be this value, which is entered in the cell C23, 0.8. Similarly, we find the solution for C34 as well, and the values entered here. All these green cells show the second stage solution. Okay. Now we go to the entries in Routh table for the second stage. Now, if you look at this entry here, 0.4, this entry 0.4 was obtained from the C12 calculation, where we found that out of k is equal to 1 or k is equal to 2, which of these cases has generated an optimal one or the minimal one? K is equal to 2 has been able to give the minimal value for the binary search tree. Hence, I would select k is equal to 2, which means B would act as a root. So what is this Routh table entry define? When 0.4 is generated as the optimal cost, when 1 and 2 are considered as the nodes to be included in binary tree, the optimal one is generated with 2 acting as a root node. And what is node 2? Its key is B, and hence B is entered. Similarly, the case is 2, 3 and 3, 4. If you notice, the optimal value here is 0.2 or the minimal value is 0.2, where k is equal to 3. So if k is equal to 3, then what is the key value? It is C, and hence in the entry 2, 3, in the corresponding entry in the Routh table, the value would be C, because k is equal to 3 has been the optimal generation. Similarly, this entry, the green entry here, is a solution for C34. C34 has given an optimal cost of 1. When you consider C34, which among these has given the optimal one? Definitely, k is equal to 3 has given an optimal one. K is equal to 3 determines the key C, and hence in the corresponding entry in the Routh table for 1, which is acting as a root node, C. So we have come to the end of stage 2, to the solution of OBST. We start with stage 3 now, where we consider all the 3 node possibilities. Although we write it as C1, 2, 3, so C2, 3, 4, we quickly redefine this as C1, 3 and C1, 3 here and C2, 4. C2, 4. So C1, 3 determines the cost of the binary search tree considering all the 3 node possibilities, which are 1, 2 and 3. So as per the recurrence definition for the OBST, so C of I, so this would be C of 1, 3, 1, 3. So I is 1, k minus 1 would be C10, plus C of k plus 1 would be 2, j would be 3. Okay, so this value would be C10 is obviously 0, plus C23 would be the value 0.8. Right? So for the second case, for the second possibility, k is 2, I remains as 1, k minus 1, which is 1, plus C k plus 1, which will be 3, j is 3. Okay, so C11 is 0.1 plus C33 is 0.4. Similarly, with k is equal to 3, I remains as 1, j will be k minus 1 would be 2, plus C of k plus 1 would be 4, j would be 3. So C12, we got an entry as 0.4 plus this entry would be 0. So plus we add the respective probabilities, search probabilities of 1, 2, and 3, which is 0.1 plus 0.2 plus 0.4. Right? So the minimum among them will be, this is 0.8, this is 0.5, and this is 0.4. So the minimum among them will be 0.4 plus this value altogether, which is 0.7, and hence this value would sum up to 1.1, which is 1, 3 would be 1.1. Okay, so we repeat the same process for the second case as shown here. So this entry is 1.1 as shown here in the diagram or the depiction below. Please have a look here. The 3 node possibilities C1, 3. We have considered the cases 1, 2, 3, and the final value would sum up to 1.1, which is the optimal cost. This is entry 1, 3. Please remember, we have to make a corresponding entry in the Routh table, and let's see the root node possibilities here. 1, 2, 3. Which among them is the minimal one? K is equal to 3, which means again the third key, which is C, has the possibility of generating the optimal binary search tree. So we have entered a C here. Okay. Similarly, consider the case 2, 4. So when we consider the case 2, 4, what are the node possibilities? In order, we would have 2, 3, 4 as the root node possibilities. So we repeat the same recurrence formula here. After solving the recurrence formula, we find that the minimum among them, this is 1, this is 0.5, this is 0.8, and hence we take up 0.5, which is the minimal value, and add along with the search probabilities, and we would end up with the value 1.4. For the corresponding root node entry, considering the optimal one here, which is the optimal one, which is giving the minimum value, it is obviously again k is equal to 3, which means the key C would act as a root node in this case. So what does this entry denote? With 1.4 as the optimal cost, considering 3 nodes as root node possibilities as 2, 3, 4, 3 has generated the optimal one, and hence we have written down C here. But the same process would be repeated in stage 4. Stage 4 with 4 node possibilities, we have only one value, which is C14. C14 here. This is the final value, and this would be the final optimal binary search tree cost. That with that, we come to the end of the optimal binary search tree construction. So if you look at the 4 node possibilities here, there are 4 possibilities, 1, 2, 3, 4, all of them generated using the recurrence, added along with your search probabilities, and we end up with the value 1.7. 1.7 as entered here, and let us once again look at what is the root node possibility minimal one. Which is the minimal one among them? Yes, obviously node C has appeared to be the minimal one. So formally we have come to the end of construction of the cost table as well as the Routh table, but there's one small job left pending, and that would be the construction of the OBST. Now in order to construct the OBST, now if you look at the solution here, 1.7 is a final cost, the OBST cost, okay, and C is the root node. So this should be your solution. Okay. Now, when we draw the OBST, we know that C has to appear as a root node. So let's quickly put it down here. C is acting as a root node. So satisfying the property of OBST, we very well know that if C is a root node, then D would naturally appear to its right. Okay. Now, what should be the possibility of the left subtree? To the left of C, we have 2 values A and B, but we have a contention as to which should appear as the root node of the left subtree, either A or B. So in order to find out the optimal among A, B are the keys in the values 1 and 2, which means we have to consider 1, 2. When 1 and 2 are considered as a nodes to be included in the tree, what would be the optimal one? B is the optimal one. B gave the optimal binary tree, and hence B is at the root and A acts as its left child node. So this is the final optimal binary search tree construction for the given instance of OBST. Thank you.